All right, so hi everyone, welcome back. A very good evening to you all. Myself, Ayush Tripathi. Currently, I am working as a mentor at Geeks and welcome you all to this post analysis discussion of the last Job-A-Thon 42. So, before starting the discussion, I want you guys to rate the entire contest on a scale of 10. That would help us to improve the upcoming problem set. Okay, so kindly please rate the entire contest on a scale of 10. That would really helpful for us to improve the upcoming problem set. How was your contest and how many problems you were able to solve? And I personally categorized this entire contest from a easy to a medium level. All the three problems were doable. The last problem uses a prime sieve technique, that is a very standard technique in a number theory. The second problem was ad hoc problem, where you need to construct an algorithm based on some observations. Don't worry, we'll discuss the solution to all the three problems. So write a quick plus one as a confirmation from your side so that we can start the discussion. And everything seems good to me. So kindly write a plus one as a confirmation so that we can start the discussion. So let me share my screen and starting with the first problem. Okay, so here someone asking what is the next step after completing this. So basically top ranker would get an interview call from a GFG team. Don't worry, we'll answer all your doubts after the discussion, but let's just first go for the discussion. So starting with the first problem, and yes, this was the first problem. Okay, let me change the template. Cool. Yeah, this one seems best to me. So this was the first problem, maximizing cardboards. In this problem, you are given an array ARR representing the side length of a cardboard. Each length can be used at most once, and you need to follow the following steps. So the first step in the same order, that is you have to first perform the first step then second step. So first maximize the number of square based cardboard which require 4 equal side length. Cool. Then second step, after performing first step, maximize the number of rectangular based cardboards from the remaining pieces. Our first priority is to maximize the number of square, and then we need to maximize the number of rectangles. And as we all know, the rectangle has opposite side equal, so each requiring two pairs of equal side length. And then we need to return the absolute difference between the number of square based cardboards and the number of rectangular based cardboards that you can make from array ARR. So for the first example, we have 6 cardboard with the length 2, then 2 cardboard with the length 1, then again a cardboard with the length 2, then again the last 2 cardboard with the length 1. So our first step is to maximize the number of squares. So here we can only form one square with the 4 cardboards of length 1. Then it is not possible to form any rectangle or any more square. So here the number of square is 1 and the number of rectangles are 0. So their absolute difference is 1. Now coming to the second example, we have a 4 cardboard with the length 1, 2 cardboard with the length 2, then 2 cardboard with the length 3. So what we can do, we can here form one square. So we can select 4 cardboard with the length 1 and we can form one square, and then I will select these 2 cardboard, that is 2 cardboard with the length 2 and 2 cardboard with the length 3 to form an rectangle. Now coming to the solution, which is a super straightforward. So let's say we have an array ARR, and let's say we have 6 cardboard with the length 3. So here I am going to write all the cardboard with the length 3 adjacent to each other, but you all know these elements can be in any order. This is just for an explanation purpose. So 6 cardboard of length 3. Then let's say we have a 4 cardboard of length 2. And then let's say 2 cardboard of length 5. Then let's say 1 cardboard of length 7. And finally, let's say 7 cardboard of maybe length, let's say 18. 7 cardboard of length, let's say 18. So here the very first thing, I need to deal with the frequency. So for that, I will declare a map. So let's first find the frequency of each and every cardboard. So at this point of time, it's better to ask the questions regarding the problem. We'll answer all your queries regarding the leaderboard rank and everything after the discussion of the problems. But at this point of time, let's prioritize the solutions. So here, first we need to find the frequency of each and every length. So how many cardboard we have of length 3? So I will declare a map, no doubt. And if you are using Java, then you can use hash map or tree map. For Python, you can use dictionary. So how many cardboard we have of length 3? It is 6. So this is my length, and this is a frequency. Then how many cardboard we have of length 2? So 4 cardboards are there of length 2. How many cardboard we have of length 5? 2 cardboard we have of length 5. Then of length 7, we have only 1 cardboard. Then of length 18, we have 7 cardboard. Then what was the first step? The first step is to form maximum number of square, right? And we all know, to form an square, we must have to pick to form one square, we must have to pick 4 cardboard of the same length. So from every length, I'm going to pick the maximum number of quadruples, that is chunks of 4. So simply divide the frequency by 4, and these many square you can form. So let's say, yeah, simply divide the frequency by 4 to form an square. This is the formula. For example, how many squares we can form of length 3 each. So basically its frequency is 6, and 6 divided by 4, take the floor value, that will be 1. So initializing this number square with 0, and here 6 divided by 4, and definitely we take a floor value, right? And after this, I need to update its frequency by the leftover cardboard, because the first step is to find the form a square. So just simply update the frequency after. Okay, just simply update the frequency by frequency mod 4, right? So here the remaining frequency is that the remaining cardboard of length 3 is 2, which is a 6 mod 4, it is equals to 2. Cool. Then the next cardboard of length 2. So here frequency divided by 4, and then update the frequency. 4 divided by 4, it is equals to 0. Now the remaining cardboard of length 2 is 0, because here I have a 4 cardboard of length 2. I will select all the 4 cardboards to form one square. Then third one, how many cardboard of length 5 we have? 2. So we cannot form any square. 2 divided by 4, which is equals to 0, and here 2 mod 4, it is equals to 2. Cool. Similarly, 7 divided by 4, not 7, but frequency divided by 4. So the frequency is 1. We don't care what is its length, and then update the frequency. So 1 mod 4, it is equals to 1. Cool. Then we have 7 cardboard of length 18. So 7 divided by 4, and yeah, 7 divided by 4. Then update the frequency. 7 divided by 4, which is equals to 3. That is, I will pick 4 cardboard of length 18 and form one square. Now we are left with only 3 cardboard of length 18. Now from here, I'm going to form a pair. I'm going to form a pair because because the next step is to maximize the number of rectangles. So just allow me 1 minute. So the next step is to form maximum number of rectangles. So to form a maximum number of rectangle, now I'm going to select a pair. How many pairs we can have? So let's declare a variable. As per my implementation, I use a variable with the name rec, and now I'm going to select how many pairs we can have. So the simply frequency for this rectangle, for this rectangle, the remaining frequency and divided by 2. This is the formula. The frequency divided by 2, I'm going to add in my variable rectangle. So the very first, so here we have 2 corresponding to key 3, that is number of cardboard of length 3 that we are left with is 2. So how many pairs we can form? 2 divided by 2, take a floor value. Then 0 divided by 2, take a floor value. Plus 2 divided by 2, take a floor value. Then 1 divided by 2, take a floor value. Then 3 divided by 2 and take a floor value. Now, if you add these values, so this is 1 plus 0 plus 1 plus 0 plus 1, which is equals to 3. That is, we can have a 3 pairs here, right? We can have a 3 pairs. So from 3 pairs, I will select 2 pairs to form one rectangle. Or I can say we may select two cardboard of length 3 and two cardboard of length 5 to form one rectangle. Or you can say we can select two cardboard of length 3 and one cardboard of length and two cardboard of length 18. So basically, in short, what I'm trying to say, no matter what is the length of your actual rectangle, the maximum number of rectangle that I can form is only one. So that is this final number and divided by 2. How many rectangles we can form? So to form one rectangle, I need two pairs of equal length. So this is the complete solution. Now let me show you the implementation here. So this is my variable square, the number of square, maximum number of square that we can form. Then variable REC, initializing this with 0. Then unordered map for the frequency. Then iterate over all the length, increment the frequency. Then this is my first step. The number of square that we can have from this cardboard, from this length is frequency divided by 4. Then update the frequency by taking a mod with 4. Then second step is to form a rectangle. So now I'm going to check how many pairs we can have. So frequency divided by 2. And finally, the number of rectangles that I can form is number of pairs divided by 2. And I need to return the absolute difference. That's why I have this equation. So I hope it is clear to everyone. The time complexity is linear and the space complexity is also linear because of this map. And since it is unordered map, so that's why the time complexity is order of n only. Now coming to the next problem, total count of x. So in this problem, given a number n and we define two functions. The first function, sum n, represent the sum of all the integers from 0 to n, or I can say the sum of first n whole numbers. So 0 plus 1 plus 2 plus 3 up to n. Then second function, XOR sum n comma x, represent the sum of bitwise XOR operation applied to all the integers from 0 to n and a given number x. So that is 0 XOR x plus 1 XOR x plus 2 XOR x up to n XOR x. And here x can take any value from 0 to n inclusive, and we need to find the sum of all such x which satisfy this condition. That is, sum of first whole number is equals to the XOR sum function for n comma x. Okay, so where to master these kind of questions? So see, for these kind of questions, there's no alternative. You must have to participate in as many contests as you can. There are something in this world, few things for which there is no alternative. You cannot learn maths, you cannot learn DSA and CP problems. You must have to practice a lot and try to give the contest. This is the best way to learn the things when you test yourself during the contest. There is no alternative, there is no any specific seed which I could recommend you to follow. Just give as many contests as you can. So I need to return the sum of all such x satisfying the equation, that is sum n is equals to XOR sum n comma x. So for n is equals to 3, how many, what is the possible values of x and what is their sum? So if you select x is equals to 0, then the value of this function XOR sum n comma x is equals to 6, which is equals to the sum of first n whole numbers. Then if you select x is equals to 1, then it is also valid. Okay, let me discuss this on a whiteboard. So here in this problem, we have two functions. The first function, sum of n, and sum of n is equals to the sum of first n whole numbers, that is 0 plus 1. Natural numbers start with 1, whole numbers start with 0, and up to n, the sum of first n whole numbers. Then we have another function. I guess this function is named as XOR sum. So XOR sum n comma x. So basically here also I will do the same thing, but before adding the values of the first n whole numbers, I will first take a XOR with x, that is a 0 XOR x plus 1 XOR x plus a 2 XOR x and up to n XOR x. This is the definition of a function. And now I need to find the sum of all such x for which sum of n is equals to XOR sum n comma x. I need to find the sum of all such n. So let me give you an example. So let's say n is equals to 3. So here in this case, what will be the value of a sum of n? So sum of n is equals to 0 plus 1 plus 2 plus 3, which is equals to 6. Now let's find the value of sum of XOR sum, basically the second function, for n comma 0, that is value of x is equals to 0. So 0 XOR 0 plus 1 XOR 0 plus 2 XOR 0 plus 3 XOR 0, and it is equals to 6. Basically, I'm using a property that 0 XOR A is equals to A. 0 XOR something is equals to something. Then let's select the value of x as 1. So that is 0 XOR 1 plus 1 XOR 1 plus 2 XOR 1 plus 3 XOR 1. So this is equals to 1 plus 0, and it is equals to 3, and it is equals to 2. So in total it is equals to 6, which is so this is also a valid value, possible value of x, that is x is equals to 1 is same as the sum of first n whole number. Then XOR sum, let's pick the value of x as 2. So 0 XOR 2 plus 1 XOR 2 plus 2 XOR 2 plus 3 XOR 2, and it is equals to 2 plus 3 plus 0 plus 1, which is equals to 6. Now let's select the final value of x as a 3. So in this case 0 XOR 3 plus 1 XOR 3 plus 2 XOR 3 plus 3 XOR 3. So 0 XOR 3, which is equals to 3, 1 XOR 3, it is equals to 2, plus 2 XOR 3, it is equals to 1, plus 3 XOR 3, it is equals to 0. So in total, it is equals to 6, which is the which is the sum of first 3 whole number. So the value of x is equals to 3 is also valid. Now you need to find the sum of all the such x. So here 4 values of x which are valid, and their sum is equals to 0 plus 1 plus 2 plus 3, which is equals to 6. So, my answer is equals to 6. And this is same as the expected output. Now let's see how we can solve this problem. So the very first thing, this is an ad hoc problem. So you need to construct an algorithm based on some observation. And here the key idea is to observe the pattern in a binary representation of numbers. So let me write the binary representation of numbers from 1 to n. So this problem was a bit tricky, and if you are a beginner, then it might be possible that you won't be come up with such kind of solutions. So let's say the value of n is equals to 7. So now I'm going to write the binary representation of all the integers from 0 to 7. That is all the 8 integer from 0 to 7. So I'm going to write in terms of 5-bit, but you all know if it is a 32 bits, then we have some leading 0 and then binary representation of 0. Then binary representation of 1, then binary representation of 2, then binary representation of 3, then a binary representation of 4, then binary representation of 5, then binary representation of 6, and finally the binary representation of 7. So now try to pay more attention. So this is bit 0, then bit 1, bit 2, bit 3, and bit 4, and up to 31 or 63 depending on the data type. Now the important thing, if for a particular bit the number of ones and the number of zeros are same in all the numbers from 0 to, basically the count of 0 and the count of 1 are same for some particular column, then no matter what the value of corresponding bit in x, the result will be always same. So what I'm trying to say, let me write this observation. This is the key observation to solve the problem. So if bit has same number of zeros and ones. Then corresponding bit in X can be anything. Either you pick 0 or you pick 1. For example, because we all know 0 XOR 1, it is equals to 0, and 1 XOR 1, 1 XOR 1 XOR 1, it is equals to 0, right? So if we have same number of zeros, and if the number of zeros and the number of ones are same, then if you pick a 0 at the corresponding bit in X, then all the zeros will remain as it is, all the ones will remain as it is, and you will get the same result for that bit, right? And let's say we select some value of X, and at this point of time, let's just only consider the bit 0. So let's say at bit 0 we pick a 0. So what will be the result? 0 XOR 0. So here what I'm trying to say, what will be the result of bit 0 for every number? So at X, at bit 0 in X we have 0. So 0 XOR 0. So this bit 0, this will remain 0, right? Then this bit 1, 0 XOR 1, which is equals to 1. So all the bits will remain as it is, right? So corresponding to this bit, the result would be same. This is what I'm trying to say. Now let's say instead of selecting the value of bit 0 in X as 0, let's say we selected 1. So now in this case, 0 XOR 1, it is equals to 1. 1 XOR 1, it is equals to 0. 0 XOR 1, 1. 1 XOR 1, 0. Then here it is 1. And 1 XOR 1, 0. 0 XOR 1, 1. 1 XOR 1, 0. So now again the number of zeros and the number of ones are same. So what I'm trying to say, if the number of ones and the number of zeros are initially same, then no matter what you pick, the result would be remain same. And once for some particular column, or I can say for some particular bit, if the number of zeros and the number of ones are not same, then you cannot carry forward the idea. So let me explain you with this example. So basically in this case, for bit 0, how many ones we have? We have four occurrence of one, and we have four number of zeros. So the number of zeros and the number of ones are same, right? So at this position, so in my variable X, at position 0, at position 0, we can select anything. Either you select 1 or you select 0. The number of bits in position 0 at all the numbers are same. In the final result, the number of bits are same. So the result would be also same corresponding to bit 0. So let's say we decided to pick 0 here. So what will be the new value? That is 0 XOR X. So I don't care what are the remaining bits. At this point of time, I'm only going to discuss for bit 0, then what will be the value of 1 XOR X, then value of 2 XOR X, then value of 3 XOR X, then 4 XOR X. So let me explain you with these example. Otherwise the okay. So 0 XOR 0. So the result is 0. 1 XOR 0, 1. Then 0 XOR 0, 0. 1 XOR 0, 1. 0 XOR 0, 0. So what I'm trying to say, if you take a XOR with 0, then the result is same. So whatever the sum generated by bit 0 is again going to same, will be going to be same, right? But let's say instead of 0, you decided to select 1. So in this case 0 XOR 1, it is equals to 1. Then 1 XOR 1, 0. Then 0 XOR 1, 1. Then 1 XOR 1, 0. Then 0 XOR 1, 1. So basically what I'm trying to say, every 0 will be converted to 1 and every 1 will be converted to 0. And if the number of ones and the number of zeros are same, so the final sum won't be changed. It will unchanged, right? This is the observation for bit 0. Cool. Now in this case, bit 0 has same numbers. Bit 0 has a same number of ones and the same number of zeros. So for bit 0, I have two possibility. Either I can pick 0 or I pick 1. The result would be remain as it is. Now for bit 1. Now for bit 1. So let's try to extend the idea for bit 1. So bit 1, in this case, bit 1 also has same number of ones and same number of zeros. So we have a 4 ones and 4 zeros, right? We have 4 ones and 4 zeros. So here also you can use the same idea. Either you pick 0 or pick 1. The final result, the final sum will remain as it is. So for bit 1 also, we have two possibility. Either pick 0 or I pick 1. Cool. Now for bit 3. So for bit 3, sorry, this, yeah, bit 3, or I can say bit with the number 2. So let's say bit with the number 2, bit 2, I can say. So for bit 2, we have 4 zeros and 4 ones, right? So for bit 2 also, I can either pick 0 or I pick 1. Then for bit 3, I have 8 zeros, right? So here now we got a case when the number of zeros are not same as the number of ones. So now we cannot extend the idea. If for bit 3, if you pick 0 here, nothing will change. But if you pick 1 here, then now you will not get the same result. You cannot satisfy this condition. That is sum of n is equals to sum of n comma x. This will not true if you mark the bit with the number 3 set in x, then this is not possible. So what I'm trying to say, you need to find the longest I can say suffix, yes, longest suffix which has all the ones. Because if this is my integer n, you don't need to care about all the integers from 0 to n minus 1. Just only care what is the initial value of n. And this is another observation. If the number is 1 here, in a variable n, if the bit is set, it simply means the number of zeros and the number of ones are same. For example, here the bit is set, so the number of zeros and the number of ones are same. Then for bit 1, the number of zeros and the number of ones are same. So here the bit is 1. Then for bit 2, the number of zeros and the number of ones are same. So here also the bit is set. Then here the bit is 0. It simply means the number of zeros and the number of ones are not same. So with these two observations, now we can just simply generalize the solution. So here the solution is, you need to find the longest suffix which has all the ones. So in this case, this is the suffix, right? Or I can also say in this way, you need to find the first position for which bit is 0. And now you can select any combination. Now you can select any combination of this suffix. That is any combination. When I say any combination, then it simply means you can select any combination of bits for these position in X. That is maybe either 0, 0, 1 or 1, 0, 0, then 1, 1, 0. Any combination, because we all know at this position at these position I can place anything, either 0, either 1. So that's why any combination is valid. Cool. So the first thing, I need to find the position from right to left. From right to left, the first position for which the bit is 0. And then what will be my answer? So let's just first have some number which has all the set bit. That is 1 left shift pose. So we all know what is the value of 1 left shift pose. So this is for this particular example, the value of 1 left shift pose is this one. That is 1 position at which we have a set bit, then followed by 3 zeros. And now if you subtract 1 here, then you will get, so this is nothing but a 1 left shift pose. This is my 1 left shift pose. And now if you subtract 1 here, then it is 0, 1, 1. So 1 left shift pose and minus 1. And as I already told you, you can select any combination of these 3 bit, and we are interested in sum, not the actual number of combination. If we were interested in actual number of combination, then we can simply say 2 multiplied by 2 multiplied by 2 multiplied by 2. It is equals to 8. But we are interested in sum. So once you figure out this thing, let's call this as a result. So result is equals to 1 left shift pose minus 1. And then you need to find the sum of these numbers. That is for n is equals to 7, you can select any value of x, 0 to 7. So now I need to find the sum of first 7 whole numbers, or I can say first 8 whole numbers, or I can say first 7 natural numbers. So this is nothing but my final answer is equals to res multiplied by res plus 1 and divided by 2. This is the formula for sum of natural numbers. Let's say you have a variable y. So what is the sum of first y natural numbers? So this is y multiplied by y plus 1 and divided by 2. I know this sounds a bit confusing, so that's why I clearly mentioned that it is an ad hoc problem, and the solution is entirely constructive. Based on the observation, you need to construct an algorithm. So this is the complete solution. Now let me show you the implementation here. So initializing the variable pose with 0. Then while the value of n is greater than 0, and if the bit is 0, right, then I will simply stop. I will simply break this. Otherwise, removing the last set bit LSB and incrementing the value of pose. And I have initialized pose with 0, assuming that bit 0 is not set. And if it is set, increment it. Then this is my variable result, that is one left shift post and -1 to get all the ones after the first zero. And we all know I can select any combination. So that's why their sum would be sum of first numbers, first rest natural numbers. Okay, can you explain in Hindi? So basically what you can do, you can watch the recording of the session and take a multiple pause and verify each and every statement which I have given. So I would suggest just to give some time. Okay, little bit confusing. Okay, I totally understand. I totally understand this problem was a little bit confusing. So at this point of time, just skip it, and after the session, just go and rewatch the recording and take a multiple pause and verify each and every statement which I have given. The key observation here is that you need to observe the pattern in a binary representation of numbers. If for some particular bit, if the number of ones and number of zeros are same, then the corresponding bit in variable x can be anything, 0 or 1. And we can extend the idea until the number of zeros are not same as the number of ones. Once we know the number of zeros are not same as number of ones, then we cannot extend the idea. But as long as number of zeros are same as the number of ones, we have two possibilities for that bit in x, either 0 or 1. Anyway, I guess this is enough for the second problem. Now coming to the last problem. And this problem is not based on algorithms, not based on any observation. It simply uses a very super simple observation, which is I guess most of you will have to figure out the observation, which is very straightforward, believe me. So count prime subsequences. So in this problem, you are given an array of a positive integer, and your task is to find the number of subsequences. We all know what is subsequence, such that the product of elements in the subsequence is a beautiful number. And a number is a beautiful whose factors apart from 1 and the number itself all are prime numbers, or the number itself is a prime number. So basically a number is a beautiful if it's all the factors apart from 1 and the number itself are a prime number, all the factors, or the number itself is a prime number. If any of these two conditions are true, then it is a beautiful number, otherwise not. And we need to find the number of subsequences of ARR such that the product of element in the subsequence is a beautiful number. And since the answer can be very large, so we need to return the answer under mod 10 power 9 plus 7. Cool. Now listen to my explanation. So let's just make a very simple observation. So the very first thing, the length of the subsequence is always less than or equals to 2. If the length of the subsequence is greater than 2, then it definitely has at least one factor which is non-prime. So let me write this thing. Length of the subsequence is always less than or equals to 2, because let's say the length of the subsequence is 3, and the subsequence has three prime numbers, and those three prime numbers are, let's say, 2, 3, and 5. So let's say this is my subsequence, the subsequence of length 3 with elements 2, 3, and 5. So what will be their product? The product of this subsequence, it is 2 multiplied by 3 multiplied by 5, which is equals to 30. Now this 30 has some non-prime factors. So non-prime factors. So what are its non-prime factors? 6, then 10, then 15. These three are non-prime factors of 30. So all the subsequence which has length greater than 2 is invalid. So this is the first observation, that is length of the subsequence is always less than or equals to 2. Now let's just break this thing. Let me just solve this problem into multiple cases. So I know the length of the subsequence is less than or equals to 2. So let's just first count how many subsequences are possible of length 1. So let's call this as a case 1. And another important thing, let's say if we have some element with the value 1. So if some element is having value 1, then it won't affect the product. If in a subsequence, if in a subsequence you will add 1, then the product, then also the product will remain as it is. So case 1 and case 2. So the case 1, that is one length subsequence. So we'll discuss at the end how to deal with the element whose value is 1. So at this point of time, let's find the number of subsequence of length 1, and without element 1. I'm not considering the elements with the value 1. So how many subsequences are possible? So let me write some example here. So let's say you have an array with element 5, then let's say 8, then let's say 7, 6, 18, and 2. So what are the elements I can pick here? What are the elements I can pick here? Whose length is 1? What are the subsequences I can pick? Whose length is 1 and it is valid? That is, product has all the factors as a prime number. So the very first thing, I can simply pick a prime numbers. So that is, my answer is simply equals to select the prime numbers, select all the prime numbers. I can pick all the prime numbers. So let's call this as a count prime. I can simply pick all the prime numbers and subsequence of length 1, which has a prime number and it is valid. Now, the second thing, I can also pick those numbers which has two prime numbers in their factors. So I can write in this way, that is, number, I can pick all those numbers with only two prime factor. So for example, in this case, what are the prime numbers we have? We have a prime number 5. So this is a subsequence which is valid. Then prime number 7, then prime number 2. So all these three subsequences are valid. Now, can I pick 8? So let's write the prime factorization of 8. which is 2 into 2 into 8, 2. So here it has a one factor which is 4. It has one factor 4, which is a non-prime, right? So I must have to pick some number which has only two prime factors. It has three prime factor, 2 into 2 into 2. So this is invalid. Now the prime factorization of 6, which is 2 into 3, prime factorization of 18, prime factorization of 18, that is a 2 into 3 into 3. So here we have two factors, that is 9 is a non-prime, 6 non-prime, but but this element 6 is valid. It has only two prime factors. So I can pick such numbers which has only two prime factors. So that is my answer for case 1 will be the count of primes plus the numbers with the two prime factors. Now let's just draw case 2 here. That is a subsequence with the length 2. Okay, so here someone asking how many marks I need to get hired in this exam. So basically it is not marks dependent, but it is rank dependent. So you can check your ranks on a leaderboard. So I guess only top 100 participants are eligible for the interviews, but I'm not sure about this. But yes, you can expect up to, if your rank is less than 100, then you can expect and call. So two length subsequence without element 1. Two length subsequence without element 1. So how many subsequences are possible of length 2? So here I must have to select a two prime numbers only. So all the combination of two prime numbers are valid. Let's say you select some non-prime number. So let's say if you select some prime number and a non-prime number. So we all know a non-prime number can also be written as a written in terms of prime number. For example, let's say a non-prime number, let's say 6, and a prime number, let's say 3. So what will be their product? So their product will be 3 multiplied by 6, and it can be written as 3 multiplied by 2 multiplied by 3. So now it has some factors which are non-prime. So what are its non-prime factors? Non-prime factors of this product. So it is 6. 6 is a non-prime. Then 9. 9 is also a non-prime. So what I'm trying to say, a length of a subsequence is invalid if it has one prime number, or if both the numbers are non-prime, then also it is invalid. So you must have to select a subsequence with the two prime numbers only, or what I can say, any combination of two non-prime two prime numbers is valid. So this type of subsequence is invalid if you have at least if you have at least one non-prime, then it is invalid. So you must have to select both the numbers as a prime. So let me write this thing, that is any combination of two prime numbers, any combination of two prime numbers is valid. So what are the combination of two prime numbers we have? So here in this case I can say 5 comma 5 comma 2. Yes, this is a valid subsequence. then 5 comma 7, then 7 comma 2. Cool. So if I generalize this, then my answer is equals to the number of prime, which is let's say count prime, the number of prime numbers, and the number of ways to select two object out of it. It's simply NCR formula. So this is my answer. This will be my answer. Count of prime C2, or basically if you solve this, then your answer is equals to count prime and multiplied by count prime minus 1 and divided by 2. It's a simple NCR formula. NCR is equals to n factorial divided by r factorial multiplied by n minus r factorial. Now you can also use the same formula to find the result. So the number of ways to select two object out of n object is n multiplied by n minus 1 and divided by 2. This is the formula. So this is my case 2. And yes, we are done. We are almost done. Now what about the numbers with the values 1, with the value 1? So those number we can we are feel free to add the integers with the value 1 anywhere. They won't change the product. So let me write this as a case 3, or I can say a final solution. So for the final solution, I can say, let's say if I have some subsequence, let's say this is my subsequence with the two elements x and y, with the two element, let's say x and y. So here I can add any frequency of 1. So maybe I add two element with the value 1, or I may add three elements with the value 1. So what I'm trying to say, adding 1 in a subsequence won't change the product. Your product will as it is. So adding this one, or do not adding this one, or adding any frequency of 1 is optional. So let me write this thing. So adding 1 do not affect the product. Right? Do not affect the product. So element with the value 1 is optional. This is optional, right? And let's say you have a x element with the value 1, that is frequency of 1 is x. So how many ways are there? So total number of ways is equals to 2 power x. We can select any subset, right? So your final answer will be case 1 plus case 2 and multiplied by 2 power x. This is your final answer. So this is the complete explanation. Now let me show you the implementation. And I am assuming you all guys know about the prime sieve, that is a sieve of Eratosthenes, to find the prime factorization of a number. So here I have declared a constant variable int n as 10 power 5 plus 5, because in the constraint it is mentioned value of n and the value of element can be up to 10 power 5 only. So that's why this is a safer side. Then my modulus 10 power 9 plus 7, then my sieve array, and here I'm using one variable flag. So just to make sure that I call this function, I call this method prime sieve exactly once for one object. Because if you call this a pre-computation method again and again, then the time complexity would be huge. So that's why I will just simply let me just comment out this thing. So basically here I'm simply saying if flag is equals to true, that is I already called this function for the pre-computation, then simply return. Then simply return, do not pre-compute this again. So the very first thing, initializing all the elements with 1, this is a simple sieve of Eratosthenes. And here sieve of I, let me write this thing here. So sieve of I will store smallest prime divisor of I. Smallest prime divisor of I. So we all know this 0 and 1 are exceptional case. 1 and 0 are neither prime nor composite. So that's why I'm filling these values with 0. Then for all the numbers from 2 to n, if p is equals to 1, if a sieve of p is equals to 1, then p is a prime number, iterate over all its multiple, and if its multiple has not been marked, then for the multiple, its smallest prime divisor is p. And then I'm updating this flag with true. That is pre-computation has done. Do not pre-compute it again. Then this is my function to count the number of prime factors, and it takes log of n base 2 time. So I'm assuming you all guys know these things. So if you do not know, then go and read some article or watch some video. That is what I recommend. Then this is my power function, power method, which uses binary exponentiation, and it will return you x to the power n in log of n base 2 time. Then this is the method that you need to complete. So I'm calling my pre-computation method prime sieve. Then this is my prime count initializing with 0, and here I will store the count of numbers which has only two prime factors and their prime factorization. Then here I'm also going to count the number of element whose value is 1. So first I'm counting the number of prime factors. So if the value of element is equals to 1, then increment the ones count. Otherwise, if the number of prime factors is 1, so it simply means it is a prime number. It has only one factor, one prime factor, or I can say the smallest prime factor is a number itself. So that's why if the count is 1, then it is a prime number. So increment the prime count. If the count is 2, then it has only two prime factors in their prime factorization. So 2 prime count plus plus. Then this is my case 1, and this is my case 2, and then we have this total, and here I am going to handle the case when the values, when we have here I can add any combination of ones, right? So the frequency of element 1 and total multiplied by 2 power frequency of element 1, and again taking the mod. Right, and finally returning this answer. So someone asking why you count 1, because I already discussed adding 1 is optional. You can add any subset of 1 in your answer. So that's why, let's say if I have x occurrence of 1, then how many subset are possible? 2 power x. So this is the complete solution, and I hope you guys have learned something new. So please hit the like button, and do let me know if you have any doubt. Otherwise, what I would suggest, just go and rewatch the recording of this session. So that's all from my end for the today's session, and it's time to wrap it. Right. So thank you everyone for joining the session, and yeah, good night. See you.